Doing weak acid, weak base equilibrium problems is just like doing any other equilibrium problem, although we will take advantage of the fact that most weak acids have relatively very low equilibrium constant values, so you'll see that we'll be able to make a further simplification in using that. So here we have a setup of weak acid HA, and it's reacting with water, thus ionizing into hydronium ion and A- anion. You can write the abbreviated equation implying that water is in the aqueous mixture, and because water doesn't show up as a liquid in the equilibrium constant anyway, you could always use that abbreviated form. So among the variables given in these problems are the equilibrium constant for the acid, the initial concentration of the weak acid, and then you'll be asked to calculate the equilibrium concentrations of the weak acid HA and of each ion, hydronium and A-. Or another permutation would be if you're given the initial concentration of weak acid HA and the equilibrium concentrations of the results of its ionizing with water, you can then be asked to calculate the value of the equilibrium constant. One final permutation, which is equivalent to the second permutation, is if they just give you the percent ionization of the weak acid HA at equilibrium. This way you could calculate the concentrations at equilibrium of each ion based on the initial concentration of HA. Anyway, for this example, we'll take a weak acid with a pretty low value for its equilibrium constant. Let's say 4.25 times 10 to the minus 5. So basically like 1 in 100,000. And we'll use an initial concentration of the acid HA of 0.200 molar. So as with any equilibrium problem, you can use an organizer. Here we'll put the concentrations above the organizer so we don't have to keep writing that. And we'll put in the initial value for the weak acid. And there's effectively 0 H+. There's really 10 to the minus 7 molar from water, but we'll factor that at the end if ever need be, which is usually never. And now we have, based on the stoichiometry, which is 1 to 1 to 1, which is generally the case for all weak acid, weak base equilibria, so that makes things relatively easy. So we have minus 1x, or just minus x, and then a 1 to 1 change, plus x, and at equilibrium the concentration is 0.200 minus x molar for the weak acid. For hydronium it's x in molarity, and for A- it is x. We now plug those expressions or values into the equilibrium constant expression, which for this acid is products over reactants to their coefficients. We have H plus concentration, A minus concentration, HA concentration. This is all at equilibrium. So we use the equilibrium line values. We have x times x, or x squared, over 0.200 minus x. And in this example, we were given the value of that ratio is 4.25 times 10 to the minus 5. So I'm going to write that out just so you see how many zeros that is. It's quite a small number. And of course you can put this in any calculator solver or program and solve for x, which will give you the concentration at equilibrium of H+, from which you can get the pH. But here's the simplification. We see that this ratio, numerator to denominator, is a very small number. That means that the denominator is much larger than the numerator, and there is some value of x that will be solved for here, but compared to 0.200, this x is negligibly small. It has to be, otherwise you wouldn't get such a low value for the equilibrium constant Ka. So this is negligibly small, not in general, but relative to 0.200. that is the simplification that we will take advantage of. So basically we are neglecting x there. Of course you can't neglect x in the numerator, there'd be nothing to solve for. X is supposed to be a small number by itself. But relative to 0.200, maybe x is 0.00001, which is really not going to change the value of the denominator once subtracted. So we rearrange the equation, cross multiply, and you get x squared equals 0.0000425 times just the 0.200. And then you square root each side of that equation. And we could say what that is equal to. That is equal to the concentration of H plus at equilibrium. It's also equal to the concentration of the anion A minus at equilibrium. So there we have it. If we were solving this generically, we could see that as long as we have a relatively higher initial concentration of the acid compared to the value of the equilibrium constant, we're going to get an expression for the hydronium ion concentration at equilibrium that's just going to be the square root of the equilibrium constant of that weak acid times the initial concentration of that weak acid. There's the equilibrium constant, there's the initial concentration. So it can come down to one step as long as you have suitable initial conditions. Now, just to show you that this could be done without a calculator as a part 1 question, we'll write things in scientific notation. You have square root of 4.25 times 10 to the minus 5 times 2.00 times 10 to the minus 1, and then you could just multiply the respective numerical and exponential parts. 4.25 times 2 is 8.50, and 10 to the minus 5 times 10 to the minus 1 is 10 to the minus 6. So now, without really needing to use a calculator, we know that the square root of 9 is 3. So you can take a pretty good guess that the square root of 8.50 is about 2.9. We'll say square root of 10 to the minus 6 is, of course, 10 to the minus 3. And that will be our hydronium or H plus ion concentration at equilibrium. For the pH, you just take the negative log of that number. And we can also do this without a calculator. We see 10 to the minus 3, so the pH is going to be 2 something, and that about 3 changes to a 5. So the pH will be 2.5 at equilibrium. Now for the most important check, let's see whether our assumption was correct. When we solve for x, which is the concentration of H plus at equilibrium, that's 2.9 times 10 to the minus 3. Was that indeed negligible compared to 0.200? Well, let's see. Check. Answer. 0.200 minus, our answer was 0.0029, and that would work out to be about 0.197. So that's maybe about 1.5% the value of 0.200, and you'll see anything less than 5% is an acceptable percent ionization with which you can neglect X relative to the initial concentration. So all of this can be done with a good deal of accuracy without a calculator. And initially, at least for practice, you can always check your answer with a calculator. Had you done this quote-unquote exact calculation, not neglecting X, and solved for X, you still would have ended up with, to two significant figures, a pH at equilibrium of 2.5.